In 1981, at a conference hosted by the Vatican, a young physicist in a wheelchair rolled up to the podium and told a room full of Jesuit priests that asking what came before the Big Bang was like asking what lies south of the South Pole. The question itself, he said, was meaningless. The universe had no boundary, no edge, no beginning in the way we understand it. Time simply curves back on itself like the surface of a sphere. There is no before. The priests sat in silence. The physicist was Stephen Hawking, and for the next 3 decades, his word on this matter was treated as gospel. Not religious gospel, obviously, scientific gospel. The kind that gets printed in textbooks and repeated in documentaries and accepted as settled truth by an entire generation of physicists. What came before the Big Bang? Nothing. The question doesn't make sense. Move on. Except not everyone moved on. While the rest of the world nodded along, a handful of physicists looked at that answer and said no, not good enough. Some of them were Hawking's own friends, some were his collaborators. One of them had literally shared a Nobel-worthy theorem with him, and each of them independently came to the same conclusion. Hawking was wrong. Not wrong about the math necessarily, but wrong about the finality. Wrong that the conversation was over. Wrong that curiosity should stop at the boundary of a clever geometric metaphor. What happened next is one of the most dramatic intellectual conflicts in the history of science. It involves broken friendships, public betrayals, careers destroyed, careers reborn, and a series of discoveries that might contain actual physical evidence of a universe that existed before ours. This is not philosophy. This is not speculation over coffee. These are people with equations and data and reputations on the line, fighting over the single most fundamental question a human being can ask. Did anything exist before existence itself? This video is the full story. Every theory, every argument, every person who staked their life's work on an answer. And by the end, you'll understand why this question, the one Hawking said was meaningless, turned out to be the most dangerous question in physics. Let's start with the battlefield. Right now, in the year 2025, there is no consensus. Let me say that clearly because it matters. There is no accepted answer to what came before the Big Bang. What there is, instead, is a war. A quiet, slow-burning, extraordinarily high-stakes war fought in the pages of academic journals, at conferences in hotel ballrooms, and occasionally in very public, very bitter interviews. The soldiers in this war are some of the most brilliant people alive. And the thing that makes it so intense is that they're not arguing about details. They're arguing about reality. About whether the universe is a one-time event or an eternal cycle. About whether our cosmos is the only one or one of an infinite number. About whether time itself has a beginning. The 5 names you need to know are these. Stephen Hawking. You know him. The most famous physicist since Einstein. The man who gave us black hole radiation, who wrote a brief history of time, who became the public face of cosmology itself. His position, the universe is self-contained. There is no boundary, no beginning, no before. The question is retired, done, closed. Roger Penrose, Hawking's oldest and closest scientific partner. Together, they proved the singularity theorems in the 1960s, the mathematical proof that the Big Bang must have been a point of infinite density. For decades, they were allies. Then Penrose proposed something that contradicted everything Hawking believed, that our Big Bang was not the beginning, but a transition. that there was a universe before ours and another before that, stretching back forever. And he claimed he could see the evidence, actual physical marks left behind by the previous universe, imprinted in the cosmic microwave background like fingerprints at a crime scene. Alan Guth, a particle physicist at MIT who in one sleepless night in 1979 scribbled an idea in his notebook that would reshape cosmology: inflation. The idea that in the first fraction of a second after the Big Bang, the universe expanded faster than the speed of light. It solved half a dozen problems in one stroke. It was elegant, it was powerful, it was almost universally accepted, and it carried a terrifying implication. If inflation happened once, it's probably still happening somewhere, right now, spawning new universes in an endless chain of cosmic bubbles. Our universe is just one bubble among an infinity of others. There is no before the Big Bang. There is only an eternal foaming ocean of creation, and we are one droplet. Andrei Linde, a Russian physicist who took Guth's idea and pushed it further than anyone thought possible. Where Guth saw inflation as a singular event, Linde saw it as the default state of reality. Eternal inflation, a multiverse that never stops producing universes. Linde spent his career building this framework, refining it, defending it. He and Guth became the twin pillars of modern cosmology: the establishment, the mainstream, the orthodoxy. And then there's Paul Steinhardt. Steinhardt is the character in this story that makes everything complicated, because Steinhardt helped build the very theory he would later try to destroy. In the early 1980s, he was one of the key architects of inflationary cosmology. He worked alongside Guth and Linde. He contributed foundational papers. He was an insider, a true believer, a member of the inner circle. And then, slowly, methodically, devastatingly, he turned against all of it. He stood up at conferences and called inflation unfalsifiable. He called it unscientific. He said the multiverse was not a prediction, but an excuse, a way to explain anything and therefore explain nothing. He proposed an alternative, a cyclic universe, driven not by inflation, but by the collision of higher dimensional membranes. And when his former colleagues pushed back, he didn't retreat. He escalated. He wrote a book, he gave interviews, he made it personal. And the community split. These 5 people, Hawking, Penrose, Guth, Linde, Steinhardt, are the main characters in a story that spans 50 years and touches the deepest question humanity has ever asked. Their answers are radically different, their methods overlap, their egos are enormous, and the data, the actual observational evidence, is just ambiguous enough to keep all of them in the fight. Here's what makes this different from every other Mysteries of the Universe video you've seen. I'm not going to list theories like items on a menu. I'm not going to say some scientists think this, other scientists think that, and leave you to pick your favorite. I'm going to show you the humans behind the equations, the moments of doubt, the flashes of insight, the betrayals and the obsessions. Because that's what this story actually is. It's not a physics lecture. It's a drama about 5 people who each believed they understood the origin of everything and couldn't all be right. Now, before we get into each of their stories, we need to understand what they're actually fighting about. And that means understanding what the Big Bang really is, not the pop culture version, the real one. Most people picture the Big Bang as an explosion, some tiny point in empty space that suddenly blew up and created the universe. That image is wrong in almost every way. There was no empty space, there was no outside. There was no moment of detonation that you could have watched from a safe distance. The Big Bang was not an event that happened at a location in space. It was an event that happened to space, all of it, everywhere, at once. Here's a better way to think about it. Imagine running the expansion of the universe backward, like rewinding a film. Galaxies rush toward each other, stars merge, gas compresses, temperature rises. Go back far enough, roughly 13.8 billion years, and everything in the observable universe, every particle, every photon, every unit of energy, is compressed into a region smaller than an atom. The density is infinite, the temperature is infinite, the curvature of space-time is infinite. This is the singularity, the point where the math breaks. And that's the key phrase. The math breaks. General relativity, Einstein's theory of gravity that describes the large-scale structure of the universe, produces infinities at the singularity. And in physics, infinity is not an answer. Infinity is a cry for help. It means the theory has reached its limit. It means something else is going on that our equations can't capture. So when we say the Big Bang, what we really mean is we can trace the history of the universe backward to an extraordinarily hot, extraordinarily dense state, and then our best theory stops working. We don't know what happened at time zero. We definitely don't know what happened before time zero. We don't even know if before time zero is a coherent phrase. And that's the crack in the wall that all 5 of our characters squeeze through. Because here's the thing about infinities in physics. Every time they've appeared before, they've turned out to be a sign that we were using the wrong theory. When classical electromagnetism predicted that a charged particle should have infinite self-energy, quantum mechanics stepped in and fixed it. When early quantum theory predicted that certain scattering amplitudes should be infinite, renormalization fixed it. Every infinity in the history of physics has been a signal, a red flag, a signpost that said, your framework is incomplete, keep digging. So the singularity at the Big Bang might not be a real feature of the universe. It might just be a flaw in general relativity. Replace GR with a better theory, a quantum theory of gravity, and the singularity might disappear. And if the singularity disappears, then time doesn't stop at the Big Bang. It keeps going, backward, into whatever came before. That whatever is what the war's about. Some physicists say, nothing came before and the question is meaningless. That's Hawking's camp. Some say, another universe came before and we can see its ghost. That's Penrose. Some say, an eternal process of inflation came before, and our universe is one product among infinite others. That's Guth and Linde. And some say, a mirror image of our universe came before, and the Big Bang was just the moment of collision. That's Steinhardt. Every single one of these answers, if true, would fundamentally change what it means to exist. This is not hyperbole. If Penrose is right, we live in a universe that is one cycle in an infinite chain, and everything we know will eventually fade to nothing and be reborn as someone else's Big Bang. If Guth and Linde are right, our universe is a tiny bubble in an infinite ocean, and the laws of physics we experience are an accident of where our bubble formed. If Steinhardt is right, the Big Bang was not a creation event, but a collision event, and the thing that collided is still out there, and it will collide with us again. If Hawking is right, none of these possibilities exist, and asking about them is a waste of time. You can see why they argued. If you're still with me, here's what happens next. We're going to take each of these 5 minds and follow their path to their answer. We'll start with Hawking, because his answer came first and defined the conversation for everyone after him. We'll see why his idea was so seductive, why it convinced almost everyone, and why it contained a flaw, or at least a gap, that one very stubborn old man in Oxford refused to ignore. That stubborn old man had a Nobel Prize, a knighthood, and an idea so radical that most of his peers thought he had lost his mind. His name was Roger Penrose. And his story starts with a pattern in the oldest light in the universe. Stephen Hawking did not start out trying to kill a question. He started out trying to answer one. In the early 1960s, Hawking was a graduate student at Cambridge, brilliant but unfocused, coasting on raw talent without a clear direction. Then two things happened almost simultaneously. He was diagnosed with motor neuron disease and given 2 years to live. And he met Roger Penrose. Penrose at that time was working on something that would change the course of physics. He was studying black holes, specifically the question of whether a collapsing star must inevitably form a singularity, a point of infinite density at the center. The prevailing view was that singularities were mathematical curiosities, artifacts of overly symmetric models. Real stars are lumpy, uneven, rotating. Surely the collapse of a real star would avoid the infinity. Penrose proved otherwise. In 1965, he published a theorem showing that under very general conditions, no special symmetry required, gravitational collapse must produce a singularity. It was a bombshell. And Hawking, watching from Cambridge, had an insight that would define his career. If Penrose's theorem worked for collapse, for matter falling inward, then it should also work in reverse, for expansion, for the universe itself. Run the expanding universe backward, and you get collapse. Apply Penrose's logic, and you get a singularity, not as a quirk of a simplified model, as a mathematical inevitability. Hawking and Penrose spent the next several years formalizing this idea. Their collaboration produced the Penrose-Hawking singularity theorems, published between 1966 and 1970. These theorems proved rigorously and with minimal assumptions that if general relativity is correct and the universe contains the amount of matter we observe, then time must have a beginning. Not figuratively, literally. The equations of general relativity, taken at face value, demand that the universe originated from a state of infinite density a finite time ago. There is a first moment. There is nothing before it. The past is not infinite. It has an edge. This was a staggering result. For centuries, the idea that time had a beginning was theology, not science. Now it was a mathematical theorem. Hawking and Penrose had proved it, together. But Hawking was not satisfied. The problem was the infinity. That singularity at the beginning of time, infinite density, infinite curvature, infinite temperature, was not really an answer. It was a breakdown. General relativity was screaming that it couldn't handle the conditions at the very beginning of the universe, just as Newtonian gravity screams when you get too close to a black hole. The singularity was a symptom of ignorance, not a description of reality. Somewhere in that first instant, in that unimaginable compression, general relativity must give way to something deeper, a quantum theory of gravity. And that became Hawking's obsession, not just to prove that the universe had a beginning, but to understand what that beginning actually looked like when quantum mechanics entered the picture. Classical general relativity says singularity, infinite density, hard stop. But quantum mechanics is famously allergic to hard stops. Quantum mechanics deals in probabilities, in fuzzy boundaries, in things that are here and there at the same time. What happens when you apply quantum fuzziness to the beginning of the universe? Hawking spent the 1970s working on this question. Along the way, he made other discoveries. Hawking radiation, the information paradox, contributions that would have made anyone else's career. But the origin question never left him, or it was the question underneath all the other questions. If you could understand the beginning, you could understand everything. In 1981, Hawking attended a conference on cosmology organized by the Jesuits at the Vatican. The conference was, in itself, a remarkable event. The Catholic Church inviting physicists to discuss the origin of the universe, decades after the awkwardness of the Galileo affair. The Church's position, broadly speaking, was compatible with the Big Bang. God created the universe at a definite moment in time. The Big Bang could be that moment. Physics and theology, for once, seemed to agree. Hawking's presentation destroyed that agreement. Working with the American physicist James Hartle, Hawking had developed a new proposal for the quantum state of the universe, the Hartle-Hawking no-boundary proposal. And its central claim was breathtaking in its simplicity and devastating in its implications. Here's the idea, stripped to its essentials. In quantum mechanics, the behavior of a particle is described by something called a wave function, a mathematical object that encodes the probability of every possible state the particle could be in. If you want to know the probability that a particle goes from point A to point B, you calculate a path integral. You add up contributions from every possible path the particle could take, weight each one by a phase factor, and the result gives you the probability. This is standard quantum mechanics. Richard Feynman developed the technique in the 1940s, and it works brilliantly. Hawking and Hartle asked, what if you do the same thing for the entire universe? Instead of asking about a particle going from A to B, ask about the universe going from what? From nothing to its current state. Calculate the path integral over all possible geometries, all possible shapes of spacetime that connect nothing to now. Add them up. The result is the wave function of the universe, a single mathematical object that encodes the probability of every possible configuration of spacetime and matter. But there's a problem. In the particle case, you have a starting point A and an ending point B, and you sum over all paths between them. For the universe, what's the starting point? If the universe has a boundary in the past, a first moment, an edge, then you need to specify conditions at that edge. What were the initial conditions? Who or what chose them? Why those conditions and not others? This is the problem of initial conditions, and it's one of the deepest problems in cosmology. Every theory of the early universe eventually runs into it. Why did the universe start the way it did? Hawking's answer was, it didn't start. There is no boundary, no edge, no initial condition. Here's how that works. In the path integral, when you sum over all possible geometries, you have a choice about what kinds of geometries to include. Hawking proposed a specific choice: geometries where time, as you go back toward the beginning, smoothly transforms into a space-like dimension. In other words, near the Big Bang, time stops being time. It becomes another direction of space. The universe doesn't have a beginning in time because near the beginning, there is no time. There are only 4 dimensions of space, curving smoothly into each other like the surface of a sphere. This is where the South Pole analogy comes from, and it's worth understanding precisely because it's both illuminating and misleading. Think of the surface of the Earth. Lines of latitude are like moments of time. As you move south, backward in time, the circles of latitude get smaller and smaller. At the South Pole, the circle shrinks to a point. But the South Pole is not an edge. It's not a boundary. It's not a wall you hit. The surface of the Earth is perfectly smooth and regular at the South Pole. It's just that south stops being a meaningful direction. You can't go further south than the South Pole, not because something is blocking you, but because the concept itself has no meaning there. In Hawking's model, the Big Bang is the South Pole of time. As you approach it, time smoothly becomes space, and the notion of before dissolves, not because it's forbidden, but because it's undefined. The geometry of the universe simply doesn't have a temporal direction in that region. Asking what happened before the Big Bang is exactly like asking what's south of the South Pole. The question presupposes a structure that doesn't exist. This is elegant. This is beautiful. And this is why Hawking's presentation at the Vatican caused such a stir. Because if the no-boundary proposal is correct, then the universe is entirely self-contained. It has no edge, no beginning, no moment of creation. It doesn't need initial conditions because there's no initial boundary to impose them on. It doesn't need a creator because there's no creation event. The universe simply is a closed, finite, smooth, four-dimensional geometry that exists timelessly as a mathematical object. Hawking later wrote about this moment with characteristic bluntness. He said the Pope told the conference attendees that it was fine to study the evolution of the universe after the Big Bang, but they should not inquire into the Big Bang itself because that was the moment of creation and the work of God. Hawking noted with amusement that he had just presented a theory in which there was no moment of creation. He was glad, he wrote, that the Pope didn't realize this because he had no desire to share Galileo's fate. The story might be slightly embellished. Hawking enjoyed a good narrative, but the substance was real. The no-boundary proposal was a direct answer to the question, what came before the Big Bang? And the answer was, the question doesn't apply. Now, why did this convince so many people? First, the math. The no-boundary proposal isn't a hand wave. It's a specific calculable framework. You can derive predictions from it about the probability of different kinds of universes, about the spectrum of density fluctuations in the early cosmos, about the likelihood of inflation occurring. It's not just philosophy dressed up as physics. It produces numbers. Second, it solved the initial conditions problem in the most radical way possible, by eliminating initial conditions entirely. No boundary means no boundary conditions. The universe selects its own starting state through the path integral. There's no arbitrariness, no fine-tuning, no need to invoke anything outside the theory. Third, and this is the part that's harder to quantify but arguably most important, it felt right, it felt complete, it offered closure. The human mind craves a final answer, and Hawking seemed to provide one. The universe is a sphere. Time is finite, but has no boundary. There is nothing outside it. There is nothing before it. Done. Finished. You can stop asking now. For nearly 20 years, the no-boundary proposal was the dominant answer to the question of cosmic origins. It wasn't the only answer. There were always alternatives circulating in the theoretical physics community, but it was the one that appeared in popular science books, in TV documentaries, in undergraduate courses. When non-physicists asked what came before the Big Bang, the answer they received, filtered through layers of science communication, was always some version of Hawking's. The question doesn't make sense. But even at the height of this consensus, there were cracks. The first crack was technical. The no-boundary proposal, for all its elegance, turned out to be extraordinarily difficult to calculate with. The path integral over all geometries is not something anyone can actually compute exactly. You have to make approximations, and different approximations give different answers. In some versions, the no-boundary wave function predicts a universe that looks like ours, large, expanding, full of structure. In other versions, it predicts a universe that's nearly empty, or one that collapses almost immediately, or one that inflates forever without forming galaxies. Which version is correct depends on technical choices that physicists argued about for decades without resolution. In 2017, a team led by Job Feldbrug, Jean-Luc Lenners, and Neil Turok published a paper arguing that when you do the path integral carefully, using the mathematically rigorous Lorentzian approach rather than the Euclidean shortcut Hawking preferred, the no-boundary proposal doesn't work. The wave function it produces is not normalizable. In plain language, the probabilities don't add up to 1. The theory predicts that the most likely universe is one with infinite inflation, which is observationally meaningless. The paper was technical and dense, but its conclusion was stark. The no-boundary proposal, as originally formulated, is mathematically inconsistent. Hawking, who was still alive when this paper appeared, pushed back. He and his collaborators published responses arguing that the Lorentzian calculation was flawed, that the Euclidean approach was correct, that the critics had made errors. The debate became heated. And then, in March of 2018, Hawking died. The greatest advocate for the no-boundary proposal was gone, and the technical questions he had been defending against remained unresolved. The second crack was philosophical, and it's the one that matters more for our story. Even if the no-boundary proposal works perfectly, even if the math is airtight and the predictions match observation, there's something deeply unsatisfying about it as an answer to what came before the Big Bang. Because what it really says is, the question is ill-posed. It doesn't answer the question, it dismisses it. And for a certain kind of mind, the kind that stays up at night staring at the ceiling, the kind that can't accept the concept doesn't apply as a final word, the dismissal feels less like wisdom and more like evasion. Imagine someone asks you, "What's outside the universe?" And you answer, "There is no outside. Space is all there is. The question doesn't make sense." That answer might be technically correct. It might be the best current science has to offer. But does it satisfy you? Or does some part of your brain keep circling back, keep insisting that there must be something, that nothing is not a real answer, that the absence of an answer is not the same as having one? Roger Penrose felt exactly that way. Penrose had known Hawking longer than almost anyone in physics. They had worked together on the singularity theorems. They had shared stages, shared ideas, shared the intellectual landscape of general relativity for decades. Penrose respected the no-boundary proposal. He understood its elegance, but he didn't believe it. Not because the math was wrong, but because he thought the whole approach was asking the wrong question. Hawking's framework was built on quantum mechanics, specifically on the path integral formulation. It treated the universe as a quantum object whose history is a superposition of all possible geometries. Penrose had deep reservations about this approach. He believed, and still believes, that quantum mechanics itself is incomplete, that the measurement problem, the fact that quantum mechanics can't explain how or why wave functions collapse, is not a technical inconvenience, but a fundamental gap in our understanding. And if quantum mechanics is incomplete, then basing your theory of the universe's origin entirely on quantum mechanics is building on sand. Instead of asking, what is the quantum wave function of the universe, Penrose asked a different question. What happens to the universe in the infinite future? And that question led him somewhere no one expected. Here's what Penrose noticed. According to current observations, the expansion of the universe is accelerating. Driven by dark energy, space is stretching faster and faster. In the far, far future, trillions upon trillions of years from now, every galaxy outside our local group will have receded beyond the cosmic horizon, moving away from us faster than light. Stars will burn out, black holes will form, then slowly evaporate through Hawking radiation. Eventually, after timescales so vast they make the current age of the universe look like a rounding error, even the last black hole will evaporate. What's left is an empty, cold, structureless void filled with nothing but scattered photons and gravitons drifting further and further apart. This is the heat death of the universe, the final state, maximum entropy. Nothing happens anymore because nothing can happen, and most physicists stop the story there. The end. But Penrose looked at that final state and saw something strange, something everyone else had overlooked. In this final state, there is no matter, only massless particles, photons, gravitons. And massless particles have a peculiar property: they don't experience time. In the framework of relativity, a photon travels from emission to absorption in zero proper time. No matter how far it goes, no matter how many billions of years pass on our clocks, the photon's own clock reads zero. Time for a massless particle does not exist. And if the only things left in the universe are massless, then the concept of time loses its meaning at the cosmic scale. You can't build a clock out of photons. You can't measure duration. The distinction between a long time and a short time disappears. And with it, the distinction between very large and very small disappears too. Because in a universe with no massive particles, there is nothing to set a scale, no ruler, no yardstick. A universe that is 1 trillion light years across and a universe that is 1/1,000,000,000th of a centimeter across are, in a very precise mathematical sense, identical. They are related by a conformal transformation, a rescaling that preserves angles and shapes but not sizes. And since there's nothing in the universe that cares about size, the transformation is physically meaningless. Both descriptions are the same physical state. Do you see where this is going? The far future of our universe, infinite, empty, featureless, devoid of scale, is conformally identical to a singularity, a point, a Big Bang. What if, Penrose asked, the far future of one universe literally becomes the Big Bang of the next? Not metaphorically, not as an analogy, as a mathematical identity. The infinite future of one cosmic era, stripped of all scale and structure, is the same geometric object as the infinitely compressed initial state of the next era. The Big Bang is not the beginning. It's a transition, a doorway between aeons, and the universe has been cycling through these transitions forever and will continue forever. No beginning, no end. No, just an infinite sequence of aeons, each one expanding from a bang to a heat death, and each heat death becoming the next bang. This is conformal cyclic cosmology, CCC, and when Penrose first proposed it in the early 2000s, almost nobody took it seriously. But Penrose had something that elevates an eccentric idea into a scientific hypothesis. He had a prediction, and predictions can be tested. If CCC is correct, if the far future of a previous aeon becomes the Big Bang of our aeon, then certain events in the previous aeon should leave traces in our universe. Specifically, Penrose predicted that the evaporation of supermassive black holes in the previous aeon would release enormous bursts of energy concentrated in spherical shells. When these shells pass through the transition to our aeon, they should appear as faint circular patterns in the cosmic microwave background. Concentric rings of slightly anomalous temperature imprinted in the oldest light we can see. And that's where things get really interesting. Because that's exactly where Penrose's story collides with Hawking's legacy, with real data, and with a controversy that's still burning today. But that's the next part of this story. In 2010, Roger Penrose did something that made a lot of physicists very uncomfortable. He published a paper claiming he had found them, the rings, the fingerprints of a dead universe, hiding in plain sight in the cosmic microwave background. The cosmic microwave background, the CMB, is the oldest light in the universe. It was released roughly 380,000 years after the Big Bang, at the moment when the universe cooled enough for atoms to form and photons to travel freely for the first time. Before that moment, the universe was a hot, opaque plasma. After it, the universe became transparent. Those first free photons have been traveling ever since, stretching with the expansion of space, cooling from a searing glow to a faint microwave whisper. Today, they fill every cubic centimeter of the universe. They come from every direction, and they are almost perfectly uniform. Almost, not quite. The CMB has tiny fluctuations, slight variations in temperature, on the order of 1 part in 100,000. These fluctuations are the most important data in cosmology. They are the seeds of everything, every galaxy, every star, every planet, every person. The pattern of hot and cold spots in the CMB tells us about the conditions in the early universe, about the density of matter and energy, about the geometry of space itself. Cosmologists have spent billions of dollars building satellites, COBE, WMAP, Planck, to map these fluctuations with increasing precision. The data is public. Anyone can download it, anyone can analyze it, and that's exactly what Penrose did. Working with the Armenian physicist Vahe Gurzadyan, Penrose analyzed the CMB data looking for a very specific pattern, concentric circles of low variance, not hot spots or cold spots, but regions where the temperature fluctuations are unusually uniform, smooth rings in an otherwise noisy sky. According to CCC, these rings would be the signatures of supermassive black hole evaporations in the previous aeon. As a black hole evaporates through Hawking radiation over unimaginable timescales, it releases energy in a roughly spherical shell. That shell, passing through the conformal transition to our aeon, would appear as a circle on our CMB sky, a ring where the temperature is slightly more uniform than the surrounding noise. Penrose and Gurzadyan reported finding exactly such circles, multiple concentric rings centered on specific points in the sky, with a degree of uniformity that they argued was statistically significant. Their paper, published on the arXiv preprint server, made a bold claim. These are not random fluctuations. These are the echoes of black holes that died in a universe that existed before ours. The reaction from the cosmological community was swift, forceful, and overwhelmingly negative. Within weeks, 3 independent groups published rebuttals. Their argument was devastating in its simplicity. They took the Planck and WMAP data, generated thousands of simulated CMB skies using the standard cosmological model, the model that assumes no previous universe, no CCC, just random quantum fluctuations amplified by inflation, and searched those simulated skies for the same kind of concentric rings. They found them everywhere. The simulated skies, which contained no signal from any previous aeon, produced circles of low variance at roughly the same rate as the real sky. Penrose's rings, the critics argued, were a statistical artifact, a pattern that looks meaningful but arises naturally from random noise. This is one of the deepest traps in science, the human brain's extraordinary ability to find patterns in randomness. We see faces in clouds, we hear messages in white noise played backward, and when we go looking for circles in a noisy dataset, we find them, because circles are everywhere in random data if you look hard enough. Penrose did not accept this criticism. He pushed back hard. He argued that the rebuttals used the wrong statistical tests, that they compared his signal to the wrong null hypothesis, that they failed to account for the specific properties he was measuring. He refined his analysis. He published follow-up papers. He found new features in the CMB that he argued were consistent with CCC, not just circles of low variance, but also anomalous points of extreme temperature that he interpreted as the final bursts of Hawking radiation from the very last black holes to evaporate in the previous aeon. He called these Hawking points, a name that carried a certain poignancy given that Hawking himself had disagreed with the entire framework. The debate has continued for over a decade, and it remains unresolved. The mainstream view is that Penrose's claimed signals are not statistically significant, that they can be reproduced in standard simulations and therefore don't require CCC as an explanation. But Penrose has never conceded, and a small number of researchers have continued to work on CCC, refining the predictions, developing new tests, looking for additional signatures that might be harder to dismiss. Here's what makes this story more than a technical dispute about statistics. It's the personal dimension, the human weight behind the equations. Roger Penrose is not a crank. He is not a fringe figure grasping at straws. He is one of the most accomplished mathematical physicists of the 20th century. He invented twistor theory. He discovered Penrose tiling, the aperiodic patterns that later turned out to describe real quasi-crystals. He formulated the Penrose process for extracting energy from rotating black holes. He developed the abstract index notation that relativists use every day. He proved the singularity theorem that launched Hawking's career. And in 2020, he was awarded the Nobel Prize in Physics for showing that black hole formation is a robust prediction of general relativity. He received this prize at the age of 89, making him one of the oldest Nobel laureates in history. This is not a man who doesn't understand statistics. This is not a man who is easily fooled by patterns in noise. And yet, a significant portion of the physics community believes he is wrong about CCC. Not maliciously wrong, not incompetently wrong, but wrong in the way that brilliant people sometimes are when they fall in love with an idea. And here's where the story gets painful. Penrose developed the singularity theorems with Hawking. Together, they proved that the Big Bang must involve a singularity, at least in classical general relativity. That work was the foundation of both their careers, but their paths diverged fundamentally on what to do about that singularity. Hawking said, "Use quantum mechanics to smooth it out." The singularity is an artifact of classical physics. In the quantum picture, there is no singularity, no boundary, no before. Penrose said, "Quantum mechanics is not the answer, because quantum mechanics itself is broken." The measurement problem, the fact that we don't understand how quantum superpositions become definite outcomes, means we can't trust quantum mechanics at the cosmological scale. Instead, look at the classical geometry. Look at what the conformal structure tells you. The singularity is real, but it's not an endpoint. It's a transition. These two positions are not just different answers, they are different philosophies of physics. Hawking trusted quantum mechanics above all else and was willing to let it dissolve the classical notion of time. Penrose trusts geometry above all else and is willing to let it override the quantum mechanical consensus. They argued about this for decades, not bitterly. They were friends, genuine friends who respected each other deeply. But the disagreement was real and fundamental. Hawking believed Penrose was being stubborn about quantum mechanics. Penrose believed Hawking was being naive about the measurement problem, and then Hawking died. And Penrose was left arguing with a legacy. This is the thing that rarely makes it into physics papers, but shapes the entire field. When a towering figure dies, their ideas don't die with them. They calcify. They become harder to challenge, not easier, because challenging the dead feels ungracious. Hawking's popular legacy, the no-boundary proposal, the South Pole analogy, the claim that before the Big Bang is meaningless, is embedded in millions of books, countless documentaries, entire curricula. Penrose is not just arguing against a theory, he is arguing against a cultural monument, and he keeps arguing. At 94 years old, Roger Penrose continues to publish papers on CCC. He continues to analyze CMB data. He continues to refine his predictions. He continues to believe with absolute conviction that the universe we inhabit is not the first and will not be the last, that the Big Bang was a rebirth, not a birth, that the evidence is there, written in the oldest light, if only people would look at it properly. Is he right? I don't know. The data as of today does not clearly support CCC, but it doesn't rule it out either. The anomalies Penrose points to, the Hawking points, the low variance circles, the large-scale features of the CMB that don't quite fit the standard model, are real features of the data. The question is whether they require a radical explanation like CCC, or whether they're just statistical flukes and selection effects. And that question depends on technical details of statistical analysis that honest, competent scientists genuinely disagree about. What I do know is this: Penrose's willingness to stake his reputation on an unpopular idea, to endure years of dismissal from colleagues he respects, to keep fighting at an age when most people have long since retired, that willingness tells you something about the kind of person who ends up pushing science forward. Not the consensus builders, not the careful incrementalists, the stubborn ones, the ones who see something in the data that no one else sees and refuse to let it go, even when the whole world tells them they're wrong. Maybe Penrose is wrong. Maybe the rings are noise and the Hawking points are artifacts, and CCC will be remembered as a beautiful but incorrect idea from a great mind at the end of a great career. That's the most likely outcome, statistically. Most bold ideas in physics turn out to be wrong, but history is full of cases where the stubborn old man turned out to be right, where the pattern everyone dismissed as noise turned out to be a signal. Continental drift was dismissed for 50 years before plate tectonics vindicated it. The cosmological constant was dismissed as Einstein's greatest blunder before dark energy proved it was real. Quasi-crystals were dismissed as impossible before Dan Shechtman won the Nobel Prize for discovering them, and it was Penrose's own tiling theory that provided the mathematical framework. So here's the score: 2 players in. Hawking says, the question is meaningless, there is no before. Penrose says, there was a before, it was another universe, and he can see its scars. They were friends, they disagreed. One is dead, the other keeps fighting. Now the story shifts. Because while Hawking and Penrose were arguing about whether the Big Bang was a beginning or a transition, a completely different group of physicists was building an answer so powerful, so comprehensive, and so strange that it would swallow the entire debate and redefine it on new terms. Their answer didn't say the Big Bang was the beginning. It didn't say it was a transition. It said it was an accident, a random quantum fluctuation in an eternally inflating superstructure. One bubble among an infinity of bubbles. And the man who first saw this possibility, the man who cracked open the door to the multiverse, did it in a single night, in a cramped apartment in 1979, and the next morning wrote 2 words in his notebook that he underlined twice. The words were spectacular realization. His name was Alan Guth, and if Hawking's answer was a closed door and Penrose's was a window into the past, Guth's answer was a trap door into infinity. But that is where we go next. Alan Guth was not a cosmologist. That's the first thing you need to understand about him, because it explains everything that came after. In 1979, Guth was a particle physicist, a postdoc actually, the academic equivalent of a temp worker. He had bounced from Princeton to Columbia to Cornell to Stanford, chasing short-term positions, publishing decent but unremarkable papers on magnetic monopoles and grand unified theories. He was 32 years old, he had no permanent job, and his career was going nowhere in particular. Magnetic monopoles, that's what started it. Not the origin of the universe, not the nature of time. Magnets. In the late 1970s, grand unified theories, GUTs, were the hot topic in particle physics. These theories attempted to unify 3 of the 4 fundamental forces into a single framework at extremely high energies. And they made a prediction. In the early universe, when temperatures were high enough for grand unification, the cooling and symmetry-breaking process should have produced enormous numbers of magnetic monopoles, heavy, stable, point-like particles that carry a single magnetic charge, a north without a south, or a south without a north. The problem was that nobody had ever found one, not a single magnetic monopole, despite decades of searching. The universe should be littered with them. It wasn't. Where did they go? Guth was working on this problem with a colleague named Henry Tye at Cornell. They were exploring whether there was some mechanism in the early universe that could dilute the monopole density, spread them out so thin that we'd never encounter one. And on the night of December 6, 1979, alone in his apartment, Guth found the answer. What if, very early in its history, the universe underwent a brief period of extraordinarily rapid expansion? Not the gradual expansion we observe today, but an explosive, exponential blow-up, the universe doubling in size every tiny fraction of a second, over and over, for an unimaginably brief but consequential interval. If this happened, any monopoles created before the expansion would be diluted to essentially zero density. They'd still exist, but they'd be spread across such an enormous volume of space that you'd never find one in the observable universe. Problem solved, but Guth immediately realized that this mechanism, which he called inflation, did far more than solve the monopole problem. It solved 2 other major puzzles in cosmology that had been bothering people for years. The first was the horizon problem. The cosmic microwave background is almost perfectly uniform in every direction. The temperature of the CMB in one part of the sky is the same as the temperature in the opposite part, to 1 part in 100,000. But here's the thing. Those 2 regions of the sky are so far apart that, in the standard Big Bang model, they could never have been in contact. Light hasn't had time to travel between them. They have no causal connection. So how do they know to be the same temperature? It's like walking into two rooms on opposite sides of the planet and finding the thermostat set to exactly the same reading, down to 5 decimal places, in rooms that have never communicated. Inflation solves this instantly. Before inflation, the entire observable universe was contained in a tiny region, far smaller than an atom, where everything was in thermal equilibrium. Everything was in contact. Everything was the same temperature. Then, inflation blew that tiny region up to cosmic scales. The uniformity we see in the CMB is not a coincidence. It's a memory. A memory of a time when the entire observable universe was a single, tiny, equilibrated patch. The second puzzle was the flatness problem. The geometry of the universe is very close to flat, Euclidean space, where parallel lines never meet. But in the standard Big Bang model, flatness is unstable. A universe that starts out even slightly curved will become more and more curved over time. For the universe to be as flat as we observe it today, 13.8 billion years after the Big Bang, it must have been flat to an absurd degree of precision at early times. Fine-tuned to 1 part in 10 to the 60, that kind of fine-tuning is, to a physicist, a scandal. It demands an explanation. Inflation provides one. During the exponential expansion, any initial curvature is stretched flat, the same way the surface of a balloon appears flatter and flatter as you inflate it. No matter how curved the pre-inflationary universe was, inflation irons it out. Flatness is not a coincidence. It's an inevitable consequence of inflation. 3 problems, 1 solution. Guth wrote in his notebook, "Spectacular realization." He underlined it twice. The next morning, he told Time. Then he told everyone. He gave seminars at SLAC, at Harvard, at MIT. The reaction was immediate and electric. Physicists recognized that inflation was not just a clever trick, it was a paradigm shift. It connected particle physics to cosmology in a way that had never been done before. It took the abstract speculative energy scales of grand unification and turned them into observable consequences in the CMB. It was testable, it was predictive, and it was beautiful. Within a year, Guth had a permanent position at MIT, the job security that had eluded him for nearly a decade. Within 5 years, inflation was the standard framework for early universe cosmology. Within 10 years, it was in the textbooks. But there was a problem with Guth's original version of inflation, a serious one. And fixing that problem required a physicist with a very different temperament, a very different background, and a very different relationship with audacity. Enter Andrei Linde. Linde grew up in Moscow during the Soviet era, trained in theoretical physics at the Lebedev Physical Institute, and spent his early career working in an environment that was simultaneously intellectually rich and politically suffocating. Soviet physicists had access to the same equations as their Western counterparts, but limited access to Western journals, conferences, and collaborations. They developed ideas independently, sometimes in parallel, sometimes ahead. Linde was one of the brightest of his generation, fiercely creative, physically imposing, with a theatrical personality and an accent that made everything he said sound like a pronouncement from on high. Linde had actually been working on inflationary ideas before Guth's paper appeared, though he didn't call it inflation, and his early models had different problems. When Guth's paper came out in 1981, Linde immediately recognized both its brilliance and its fatal flaw. The flaw was this. In Guth's original model, inflation ends through a process called bubble nucleation. The inflationary state is like a supercooled liquid, metastable, waiting to transition to a lower energy state. The transition happens through the formation of bubbles of true vacuum within the inflating false vacuum, just like bubbles of steam forming in superheated water. The problem is that these bubbles form separately, expand and collide, and the collisions are violent. They produce a universe that is wildly inhomogeneous, nothing like the smooth cosmos we observe. Guth himself recognized this problem and called it the graceful exit problem. Inflation was spectacularly good at starting. It was terrible at stopping. Linde solved it. In 1982, he proposed what he called new inflation, later refined into chaotic inflation, in which the inflationary field doesn't tunnel out of a false vacuum, but instead rolls slowly down a potential energy slope. The transition is smooth, not violent. Inflation ends gracefully, gently, producing a universe that is hot, dense, and uniform, exactly what we observe. No bubble collisions, no catastrophic inhomogeneities, a clean exit. But chaotic inflation came with a feature that Linde initially saw as a curiosity and later realized was the most important thing about it. In Linde's model, inflation doesn't have to start everywhere at once. It can start in a tiny patch of space where the inflatant field happens to have a high enough value. That patch inflates, becomes enormous, and eventually stops inflating, becoming a universe like ours. But here's the key. While our patch is winding down, other patches further away might still be inflating, and within those inflating patches, random quantum fluctuations can kick the inflatant field back up to high values, triggering new rounds of inflation. New patches blow up, become enormous, slow down. But within each of those, new fluctuations trigger new inflations, and so on. Forever. This is eternal inflation, and it changes everything. In eternal inflation, the Big Bang of our universe is not the beginning of reality. It's a local event. One patch of an eternally inflating space-time stopped inflating and became what we call our cosmos. But the larger structure, the inflating background, never stops. It can't stop. The quantum fluctuations that restart inflation are probabilistically guaranteed to occur somewhere, always, producing new pocket universes in an endless self-reproducing process. Our universe is a bubble in an infinite foam. There are other bubbles, infinitely many. Each one might have different physical constants, different particle content, different numbers of spatial dimensions. The multiverse. If you're watching this video and you've ever heard the term multiverse in a physics context, not the Marvel kind, the real kind, this is where it comes from. Not from string theory, though string theory later provided a landscape of possible vacua that dovetailed perfectly with eternal inflation. The original idea, the mechanism that generates an infinity of universes, came from Andrei Linde's chaotic inflation in the early 1980s. Now, let's pause and understand what this means for our central question. What came before the Big Bang? In the inflationary framework, the answer is more inflation. Our Big Bang was the moment when our local patch of the inflatant field decayed, releasing its energy as hot matter and radiation. Before that moment, our patch was inflating. Before that, it was part of a larger inflating region. Before that, another larger region. The chain extends backward without limit, or at least that's the default picture. Eternal inflation is eternal in both directions, future and past. New universes are always being born. The process never started because it was always happening. Except that last part might not be true. In 1993, Arvind Borde and Alexander Vilenkin proved a theorem suggesting that even eternal inflation must have a past boundary. The inflating spacetime cannot be extended infinitely far into the past. It must have had a beginning, even if everything since that beginning has been an eternal process. This is the Borde-Guth-Vilenkin theorem, later refined in 2003 with Guth as a co-author. And it's one of the most important and underappreciated results in modern cosmology. It says eternal inflation can provide an infinite future, but not an infinite past. Something must have started the process. Guth himself has been remarkably candid about this. In interviews, he's acknowledged that inflation doesn't answer the ultimate question of origins. It pushes the question back, way back past our Big Bang, past our pocket universe, into the deep structure of the eternally inflating multiverse. But it doesn't eliminate it. Somewhere, somewhen, inflation had to start. And what started it? What are the initial conditions for eternal inflation? Nobody knows. But what Guth and Linde did achieve is this. They made before the Big Bang scientifically meaningful. Hawking said the question was ill-posed. Guth and Linde said, no, the question makes perfect sense. Before our Big Bang, there was an inflating space-time. It's a physical thing. It obeys laws. We can describe it mathematically. We can derive predictions from it, predictions about the statistics of CMB fluctuations, about the geometry of space, about the distribution of matter. And those predictions have been spectacularly confirmed. The CMB fluctuations predicted by inflation, their spectrum, their distribution, their statistical properties, match the data from the Planck satellite with extraordinary precision. Inflation is not a speculative hypothesis. It is the most successful theory of the early universe we have. Its predictions have been tested and confirmed to a level of accuracy that rivals particle physics experiments. If you're still here, I want to make sure you understand the scale of what Guth and Linde built. In the span of about 5 years, from 1979 to 1983, two physicists, one an unemployed American postdoc, the other a Soviet theorist working behind the Iron Curtain, constructed a framework that explained the large-scale structure of the universe, resolved multiple long-standing puzzles in cosmology, made testable predictions that were later confirmed by billion-dollar satellite missions, and along the way implied that our entire observable universe, everything we can see or ever will see, is an infinitesimal speck in an incomprehensibly larger structure. A structure that is still growing, a structure that will never stop growing, a structure in which new universes are being born right now, every instant, in regions of space so far away that their light will never reach us. That's inflation. That's the mainstream answer to what came before the Big Bang. It's not nothing. It's not a previous universe. It's an eternal, self-reproducing, universe-generating machine. And our Big Bang was just one of its products. By the mid-1990s, this picture, inflation plus the standard cosmological model, was the consensus, the concordance cosmology, the textbook answer. Guth and Linde were celebrated, prize-laden, tenured at top institutions. Inflation was taught in every graduate program in the world. It was the framework within which all other cosmological questions were posed and answered. And then, at the height of this triumph, one of the architects looked at what he had built and said, "This is wrong." If you've been keeping count, that's the third time in this story someone has looked at a seemingly airtight consensus and refused to accept it. Hawking built the no-boundary proposal, and Penrose rejected it. The standard Big Bang model was the consensus, and Guth overturned it with inflation. Now inflation was the consensus, and the man who stepped forward to challenge it was not an outsider. He was not a rival from a competing school of thought. He was one of the founding fathers. His name was Paul Steinhardt. And his rebellion didn't just challenge inflation, it threatened to tear apart the entire community that had been built around it. I want you to leave a comment right now. Tell me, based on what you've heard so far, which answer do you find most compelling? Hawking's no boundary, Penrose's cyclic universe, or Guth and Linde's eternal inflation? I'm genuinely curious, because the next part of this story is about a man who knew all three answers intimately and decided none of them were good enough. His argument would shake cosmology to its foundations, and his former friends would never forgive him for making it. Paul Steinhardt's betrayal, and I use that word deliberately because that's how many of his colleagues experienced it, did not happen overnight. It was slow, methodical, almost surgical. And it began with a question that sounded innocent. It turned out to be devastating. The question was, what does inflation actually predict? On the surface, this seems absurd. Inflation predicts a flat universe. Confirmed. Inflation predicts a nearly scale-invariant spectrum of density fluctuations. Confirmed. Inflation predicts that the CMB should be almost perfectly uniform with tiny Gaussian perturbations. Confirmed. The predictions of inflation have been verified to exquisite precision by COBE, WMAP, and Planck. So what's the problem? The problem, Steinhardt argued, is that inflation doesn't predict these things, not uniquely, not inevitably. What inflation actually does is accommodate them, which is a very different thing. Here's what he means. Inflation is not a single theory. It's a framework, a class of models. To make inflation work, you need an inflatant field, a scalar field that drives the exponential expansion. But the theory doesn't tell you what the inflatant is. It doesn't tell you what its potential energy function looks like. It doesn't tell you its initial conditions. These are free parameters, choices that the theorist makes, and depending on what choices you make, you can get almost any outcome you want. Want a flat universe with scale-invariant fluctuations? Choose this potential. Want a curved universe with non-Gaussian fluctuations? Choose that potential. Want a universe that inflates for a long time? Adjust this parameter. Want one that barely inflates at all? Adjust it differently. The space of possible inflationary models is enormous, effectively infinite, and within that space you can find a model that produces virtually any observation. This is the heart of Steinhardt's critique, and it cuts deep. A theory that can predict anything predicts nothing. If no observation can rule out inflation, because for any observation there exists some inflationary model that produces it, then inflation is not a scientific theory in the Popperian sense. It is not falsifiable. It is, Steinhardt would later write, a theory of anything. And a theory of anything is a theory of nothing. Now, to be fair, not all inflationary models are created equal. The simplest models, the ones with the fewest free parameters, the smoothest potentials, the most natural initial conditions, do make specific predictions, and those predictions have been confirmed. Proponents of inflation argue that this is exactly how science works. You start with the simplest version, you test it, and if it passes, you accept it. The fact that more complicated versions exist and could produce different outcomes is irrelevant as long as the simple version works. Steinhardt's response to this was sharp. The simple version works, he said, but only because we chose to look at the simple version. We have no theoretical reason to prefer simple inflationary models over complicated ones. The inflatant field is not a known particle. Its potential is not derived from any fundamental theory. We chose the simple potential because it fits the data, and then we celebrated when it fit the data. That's not prediction. That's curve fitting. And then he went further. He attacked the thing that Guth and Linde considered inflation's greatest triumph, the multiverse. Remember, in eternal inflation, quantum fluctuations keep restarting inflation in distant regions of space, producing an infinite number of pocket universes. Each pocket universe can have different physical constants, different particle content, different laws of physics. This is the multiverse. And for Guth and Linde, it was a feature, not a bug. It explained why the constants of our universe seem fine-tuned for life. Among infinitely many universes with different constants, we necessarily find ourselves in one where the constants allow our existence. This is the anthropic principle, and in the context of the multiverse, it transforms fine-tuning from a mystery into a statistical inevitability. Steinhardt looked at this and saw a catastrophe. If there are infinitely many pocket universes with every possible combination of physical constants, then the anthropic principle can explain anything. Why is the cosmological constant so small? Because in most universes it's large, and those universes are lifeless, but we happen to be in a rare one where it's small. Why do we have 3 generations of quarks? Same logic. Why is the proton mass what it is? Same logic. Every question about the fundamental constants of nature gets the same answer, because if they were different, we wouldn't be here to ask. This is not science, Steinhardt argued. This is the end of science. If every observation can be explained by saying, "It had to be this way for us to exist," then no observation can ever surprise us. No experiment can ever teach us anything fundamental. The entire enterprise of theoretical physics, the search for underlying principles that explain why the universe is the way it is, becomes meaningless. We stop looking for reasons. We stop looking for deeper laws. We shrug and say, "It's the multiverse. It could have been anything. It happens to be this." Steinhardt articulated this argument in a series of increasingly pointed papers and talks throughout the 2000s. But the moment that transformed the argument from a technical debate into a public confrontation came in 2011, when Steinhardt published a provocative article in the journal Nature. The title made his position unmistakable. He was calling for the end of inflation as the dominant paradigm. The response from the inflationary establishment was furious. Guth pushed back in public talks, arguing that Steinhardt was mischaracterizing inflation, that the simplest models are well-motivated and testable, and that the multiverse, while speculative, is a legitimate scientific hypothesis, not a cop-out. Linde was less diplomatic. In interviews, he accused Steinhardt of intellectual dishonesty, of distorting the arguments to suit his agenda, of attacking a straw man version of inflation that no serious practitioner actually held. The conflict became personal. At conferences, the atmosphere in sessions on inflation became tense. Physicists who had been friendly for decades started avoiding each other. Steinhardt later described the experience in stark terms. He said that he lost friends, that colleagues who had worked with him for years stopped returning his calls, that invitations to certain conferences dried up, not because anyone sent a formal notice of exclusion, but because the informal networks that govern academic life, the dinner invitations, the workshop organizing committees, the refereeing of each other's papers, quietly contracted around him. This is the part of science that nobody talks about in popular accounts, the social machinery, the tribal dynamics. Science is supposed to be a dispassionate search for truth, but scientists are human, and humans form tribes. The inflationary community was a tribe. It had its leaders, its orthodoxies, its heroes, its origin story. And Steinhardt, a founding member, a former insider, was committing the one sin that tribes never forgive: apostasy. But Steinhardt was not just tearing down, he was building something. Starting in 2001, working with Neil Turok, a South African-born cosmologist then at Cambridge, Steinhardt developed an alternative to inflation, a radically different picture of the universe that, if correct, would answer the question, what came before the Big Bang, in a way that none of the other frameworks did. The idea was called the ekpyrotic model, and later, in its more developed form, the cyclic model. Here's the basic concept. Imagine that our universe, all three spatial dimensions of it, is a membrane, a brane in the language of string theory. This brane exists in a higher dimensional space, a bulk that contains at least one additional spatial dimension, and in that bulk there is another brane, parallel to ours, separated by a tiny gap in the extra dimension, a shadow world, hovering just a hair's breadth away from us in a direction we can't point to. Now imagine that these two branes are attracted to each other. They drift closer, slowly at first, then faster, and then they collide. The collision is the Big Bang. When the two branes smash together, the kinetic energy of their approach is converted into matter and radiation. The collision fills each brane with a hot, dense plasma, exactly the same hot, dense state that we observe at the beginning of our universe. The brane rebounds, the two branes fly apart, the universe expands and cools, structures form, stars ignite, planets coalesce, life evolves, and then, over enormous timescales, the branes slow down, stop, and begin drifting toward each other again. Another collision, another Big Bang, another cycle. In the cyclic model, the universe has no beginning and no end. It oscillates between Big Bangs, each one a collision between branes, each one producing a new period of expansion and cooling and structure formation. The time between collisions is roughly 1 trillion years, long enough for stars to burn out and the universe to become cold and empty before the next collision resets everything. This is superficially similar to Penrose's CCC. Both are cyclic, but the mechanism is completely different. Penrose's cycles are driven by conformal geometry and the loss of mass. Steinhardt's cycles are driven by brane collisions in extra dimensions. Penrose's model is built on classical general relativity and conformal invariance. Steinhardt's model is built on string theory and M theory. They arrived at similar conclusions from entirely different starting points. And like Penrose, Steinhardt claimed that his model could explain everything inflation explains: flatness, homogeneity, the spectrum of CMB fluctuations without inflation. In the cyclic model, the universe is flat because it has had an infinite number of cycles to flatten out. The universe is homogeneous because the slow approach of the two branes is an extraordinarily gentle process that smooths out any inhomogeneities. The density fluctuations that seed galaxies are produced not by quantum fluctuations during inflation, but by quantum fluctuations in the inner brane distance during the approach phase. The predictions are similar. Not identical, but similar enough that current data cannot clearly distinguish between them. The key difference, Steinhardt argued, is philosophical. Inflation leads to the multiverse and the death of predictability. The cyclic model does not. In the cyclic model, there is one universe, undergoing one cycle after another, governed by one set of physical laws. There is no landscape of possibilities. There is no anthropic principle needed. The constants of nature are what they are because the dynamics of the cycles select them, not because we got lucky in a cosmic lottery. This is the core of Steinhardt's pitch. The cyclic model preserves the scientific method. It keeps the game alive. It says there are reasons for everything and we can find them. Whether this pitch is convincing depends on who you ask. Guth and Linde argued that the cyclic model has its own fine-tuning problems, that it relies on string theory ideas that are even more speculative than inflation, and that its predictions for the CMB are not clearly distinguishable from inflation's. They also point out that the cyclic model has not been developed to the same level of mathematical rigor as inflation. It's a sketch, they say, not a theory, an aspiration, not an achievement. Steinhardt counters that inflation's apparent rigor is an illusion, that the multiverse has hollowed it out from within, and that the cyclic model, while less developed, is at least asking the right questions. And here is where we stand. Two camps, both led by towering intellects, both armed with equations and data, unable to resolve their disagreement. And the reason they can't resolve it is that the data is not yet good enough. Both inflation and the cyclic model predict nearly identical CMB power spectra. Both predict a flat universe with Gaussian perturbations and a spectral index very close to 1. The differences are subtle. They show up in things like the ratio of tensor perturbations to scalar perturbations, the so-called tensor to scalar ratio. Inflation, in its simplest versions, predicts detectable gravitational waves from the early universe. Ripples in spacetime produced during the inflationary expansion, imprinted in the CMB as a specific polarization pattern called B-modes. The cyclic model predicts that these gravitational waves should be undetectably small, essentially zero. This is a clean binary test. If we detect primordial B-modes, inflation wins and the cyclic model is dead. If we don't detect them, even with increasingly sensitive instruments, inflation doesn't die. There are inflationary models that predict small gravitational waves too, but the cyclic model survives and gains credibility. The hunt for B-modes has been one of the great dramas of modern observational cosmology. In March of 2014, a team using the BICEP-2 telescope at the South Pole announced that they had detected them. Primordial gravitational waves, the smoking gun of inflation. The discovery was hailed as one of the greatest in the history of physics. Guth and Linde were photographed in tears. The internet erupted. Nobel Prizes seemed assured. Then, within months, the result fell apart. It turned out that the BICEP-2 team had underestimated the contribution of galactic dust, ordinary dust grains in our own Milky Way that emit polarized light mimicking the B-mode signal. When the Planck satellite team released their dust maps later that year, it became clear that the BICEP-2 signal could be entirely explained by dust. There were no primordial gravitational waves, or if there were, they were buried too deep beneath the dust for BICEP-2 to find. The retraction was devastating. Not just for the BICEP-2 team, whose careers were bruised by the premature announcement, but for the entire inflationary community. The smoking gun had turned out to be smoke and mirrors, and Steinhardt, who had watched the announcement with skepticism from the start, allowed himself a quiet moment of vindication. Not because inflation was wrong, the data didn't show that, but because the rush to confirm inflation had led serious scientists to make serious errors. The desire to validate the paradigm had overwhelmed the discipline of careful analysis. As of today, no primordial B-modes have been detected. Next-generation experiments, CMB-S4, Lightbird, and others, are being designed to push the sensitivity by orders of magnitude. Within the next decade, we may have an answer. If B modes are found, Steinhardt's cyclic model is ruled out. If they're not found, the debate continues, but on terms increasingly favorable to Steinhardt. Think about what that means. A man who helped build the dominant theory of modern cosmology, who turned against it on principle, who endured years of professional isolation and personal attacks, might be vindicated or definitively refuted within a few years. The stakes are not abstract. They are career-defining, life-defining. And here's the part that stays with me. I've read interviews with all three of these men, Guth, Linde, Steinhardt. Guth is measured, careful, diplomatic. He acknowledges the multiverse problem, but frames it as an open question, not a crisis. Linde is passionate, combative, absolutely certain that eternal inflation is correct and that the multiverse is real, whether or not it makes philosophers uncomfortable. And Steinhardt is something else entirely. There's a quality to his arguments that goes beyond professional disagreement. He speaks about the multiverse the way someone might speak about a betrayal, because for him, it is a betrayal. He helped create inflation because it made cosmology more scientific, more predictive, more testable, more constrained. And then he watched as eternal inflation and the multiverse turned it into something he considers less scientific. A framework that explains everything and therefore explains nothing. If you're watching this and you're enjoying this journey through the biggest ideas in physics, do me a favor. Hit subscribe. Not because I'm asking for numbers, but because this kind of deep dive content, 2 hours on a single question, no shortcuts, no clickbait simplifications, only keeps getting made if people actually show up for it. And I want to keep making it. So subscribe and let's keep going, because we're not done yet. We've now heard from Hawking, Penrose, Guth, Linde, and Steinhardt. 5 minds, 4 radically different answers, no boundary, cyclic aeons, eternal inflation, brane collisions, and the data maddeningly cannot yet distinguish between them. But the story doesn't end with these 5, because while they were arguing, while Penrose was searching for rings and Steinhardt was battling Linde, and Guth was waiting for B modes, a new generation of physicists was developing answers that none of the old guard had imagined. Answers built on quantum gravity, on loop quantum cosmology, on ideas so strange and so new that they don't yet have the weight of decades behind them. But they might have the future, and that's where we go next. There's a question hiding behind all the answers we've discussed so far. You might have noticed it. Every single framework, Hawking's no-boundary proposal, Penrose's cyclic cosmology, Guth and Linde's eternal inflation, Steinhardt's brane collisions, shares one uncomfortable feature. They all, in one way or another, dodge the singularity. Hawking dissolves it by turning time into space. Penrose leaps over it by connecting one aeon's infinite future to the next aeon's Big Bang. Guth and Linde push it back into the infinite past of an eternally inflating multiverse. Steinhardt replaces it with a collision that, in the mathematics of extra dimensions, is smooth and non-singular. But none of them actually resolve it. None of them start from the singularity itself, that point of infinite density, infinite curvature, infinite temperature where general relativity breaks down, and show you what it really is. What it looks like when you have a theory that doesn't break. What happens at time zero when the math doesn't scream and give up. To do that, you need quantum gravity. Not quantum mechanics applied loosely to cosmological questions, which is what Hawking did. Not string theory in its vast, untestable landscape, which is where Steinhardt went for his brane model. You need a theory that directly, explicitly quantizes the geometry of space-time. That takes the smooth, continuous fabric of Einstein's general relativity and replaces it with something discrete, granular, fundamentally quantum mechanical at the smallest scales. Two approaches to this problem have dominated the last 30 years. String theory is one, loop quantum gravity is the other. And while string theory gets most of the popular attention, it's the one with the elegant mathematics, the celebrity physicists, the best-selling books. It's loop quantum gravity that has produced the most concrete, most specific, most testable answer to the question of what happened at the Big Bang. The answer is called the Big Bounce. Loop quantum gravity, LQG, was developed starting in the mid-1980s by Abhay Ashtekar, Carlo Rovelli, and Lee Smolin, building on earlier work by Amitabh Sen. The core idea is disarmingly simple in concept, even though the mathematics is ferociously difficult. In general relativity, space-time is a smooth continuum. You can zoom in forever and it stays smooth. There is no smallest length, no smallest volume, no granularity. Space is infinitely divisible. LQG says, no, it isn't. In loop quantum gravity, space itself is quantized. It comes in discrete chunks, in the same way that energy comes in discrete chunks in ordinary quantum mechanics. There is a smallest possible volume, roughly the Planck volume, about 10 to the minus 99 cubic centimeters. There is a smallest possible area. There is a smallest possible length. Below these scales, the concept of geometry, as we know it, ceases to exist. Space-time is not a smooth fabric. It's a network, a spin network, in the technical jargon, of discrete nodes connected by links, each carrying quantum numbers that encode the geometry of tiny patches of space. At everyday scales, this discreteness is utterly invisible. The Planck length is so inconceivably small, 20 orders of magnitude below the diameter of a proton, that the continuum approximation of general relativity is spectacularly accurate for all practical purposes. It's like treating water as a continuous fluid, even though it's really made of molecules. At large scales, the approximation is perfect. At molecular scales, it breaks down. The Big Bang is where the approximation breaks down. In the early 2000s, Abhay Ashtekar and his collaborators, Martin Bojewald, Parampreet Singh, and others, applied the techniques of loop quantum gravity to cosmology. The result was loop quantum cosmology, or LQC. And the first thing they discovered was that the singularity disappears. Here's why. In classical general relativity, as you rewind the universe toward the Big Bang, the density increases without limit. It goes to infinity. That's the singularity. But in LQC, there's a maximum possible density, roughly the Planck density, about 5 times 10 to the 96 kilograms per cubic meter. When the universe reaches this density, the quantum geometry of space-time generates a repulsive force. Not a force from matter or energy, but a force from the fabric of space itself. The discreteness of space at the Planck scale creates an effective pressure that resists further compression. And what happens when an irresistible compression meets an immovable quantum geometric resistance? The universe bounces. The Big Bounce. Instead of a singularity, infinite density, breakdown of physics, here be dragons, you get a smooth transition. The universe contracts to Planck density, hits the quantum geometric wall, and rebounds into expansion. Our Big Bang is the rebound, and before the rebound, there was a contracting universe, a previous phase, a before. This is a fundamentally different kind of answer from everything we've discussed. Hawking said there is no before. Penrose said before was a conformally related aeon. Guth said before was more inflation. Steinhardt said before was a brane approaching from extra dimensions. LQC says before was a contracting universe, possibly very much like our own, that shrank until quantum geometry stopped the collapse and turned it into expansion. The symmetry is striking. In the simplest LQC models, the post-bounce universe is a nearly mirror image of the pre-bounce universe. Time reversed. What we experience as expansion from a Big Bang, an observer in the pre-bounce phase would experience as contraction toward a big crunch. They would see their universe shrinking, compressing, heating up, and then, at the moment of maximum compression, instead of being crushed into a singularity, bouncing back into what we call our Big Bang. From their perspective, our universe emerged from the death of theirs. From our perspective, their universe is the ghost that preceded ours. Is this testable? This is the question that separates a real scientific hypothesis from philosophical speculation. And the answer, remarkably, is yes, at least in principle. The Big Bounce leaves signatures. During the bounce, when the universe is at Planck density, the quantum geometric effects modify the spectrum of primordial perturbations, the tiny density fluctuations that later become galaxies. In standard inflation, these perturbations are generated during the inflationary expansion and have a nearly scale-invariant spectrum. In LQC, the perturbations also end up nearly scale-invariant. Inflation still happens after the bounce, driven by the same inflaton field, but with specific corrections at the largest scales. The very longest wavelength perturbations, the ones that span the entire observable universe, carry imprints of the bounce. Their amplitude and phase are modified by the quantum geometry in calculable, predictable ways. These corrections show up in the CMB. Specifically, they affect the lowest multipoles, the largest scale patterns in the cosmic microwave background. And here's where it gets interesting. The observed CMB has anomalies at the largest scales. The quadrupole, the second lowest multipole, is lower than the standard inflationary model predicts. The octupole is oddly aligned with the quadrupole in a way that standard cosmology doesn't explain. These anomalies have been noted since WMAP and confirmed by Planck. They're not large enough to be definitive. They could be statistical flukes. But they're there, and they're exactly the kind of feature that LQC predicts. Ivan Agulo, working with Ashtekar and William Nelson, published detailed calculations showing that loop quantum cosmology can naturally account for these large-scale anomalies. The bounce modifies the initial conditions for inflation in a specific way that suppresses power at the largest scales and introduces correlations between the quadrupole and octupole. The fit is not perfect, nothing in cosmology ever is, but it's suggestive. It's the kind of hint that makes you want to look harder. But let me be honest about the limitations. Loop quantum cosmology is not loop quantum gravity. Full LQG is a theory of quantum geometry in all its complexity. Spin networks, spin foams, a vast and still developing mathematical framework. LQC is a simplification. It takes the full theory and reduces it to a cosmological setting, keeping only the degrees of freedom that are relevant for a homogeneous, isotropic universe. This simplification is necessary because the full theory is too complicated to solve exactly for cosmological scenarios. But it means that the predictions of LQC depend on the validity of the simplification. And whether that simplification captures the essential physics is an open question. Critics of LQC, and there are many, particularly in the string theory community, argue that the theory is too simple to be trusted. that the Big Bounce might be an artifact of the homogeneous approximation, not a robust prediction of the full theory. That when you add inhomogeneities, anisotropies, and the full complexity of quantum geometry, the bounce might not survive. These criticisms are serious and have not been fully answered. Proponents counter that the bounce is robust. It has been shown to survive the addition of anisotropies in Bianchi models, which are the simplest inhomogeneous generalizations of the standard cosmological model. And they point to the growing body of results from spin foam cosmology, a more fundamental approach that attempts to derive the bounce from the full LQG framework, as evidence that the bounce is not an artifact. The debate is ongoing. It is technical, detailed, and far from resolution. But what matters for our story is this. Loop quantum cosmology provides a concrete, mathematically well-defined, observationally testable mechanism for a universe before the Big Bang. It doesn't require extra dimensions, branes, conformal rescaling, or an eternal multiverse. It requires only that space-time, at the very smallest scales, is discrete rather than continuous, quantized rather than smooth. And that single assumption, supported by the full apparatus of loop quantum gravity, is enough to replace the singularity with a bounce and open a window into a pre-Big Bang universe. Now, LQC is not the only new contender. In string theory, there is a proposal called string gas cosmology, developed by Robert Brandenberger and Kumrun Vafa. The idea is that in the very early universe, all spatial dimensions were compact and filled with a hot gas of strings. Some of these strings were wound around the compact dimensions, preventing them from expanding. As the universe cooled, the wound strings annihilated each other, but only in 3 dimensions, because string annihilation requires strings to find each other, and in more than 3 spatial dimensions, the probability of intersection drops to 0. So 3 dimensions expanded, becoming our 3 dimensions of space, while the others remained compact. The Big Bang, in this picture, is the moment when 3 dimensions broke free and started growing. String gas cosmology has its own predictions for the CMB, a spectrum of perturbations that is nearly scale invariant, but with a slight blue tilt at the very largest scales, opposite to the red tilt predicted by inflation. Current data favors the red tilt, which is a problem for string gas cosmology. But the model's not dead. It's being refined and developed, and its proponents argue that the current data is not precise enough at the largest scales to be definitive. There are other proposals too. The no-boundary idea has been revived in new forms by James Hartle and Thomas Hertog, Hawking's last collaborator, who published a major paper with Hawking just weeks before Hawking's death in 2018. This paper proposed a revised version of the no-boundary proposal using the holographic principle from string theory, and it made a startling prediction. The universe is finite, not infinite, and the multiverse, if it exists, is far simpler and more constrained than the eternal inflation picture suggests. Hertog has continued developing this framework, calling it a tamer version of the multiverse, one that is potentially testable because it limits the number and variety of pocket universes. There's Alexander Vilenkin's tunneling proposal, an alternative to Hawking's no-boundary idea in which the universe tunnels from literally nothing into existence, the way a quantum particle tunnels through a barrier. In Vilenkin's picture, nothing is not empty space. It's the absence of space, time, matter, and energy, total nothingness, and the universe pops into being from this nothingness through a quantum fluctuation. No cause, no reason, no trigger, just the laws of quantum mechanics operating on the void. This idea has a strange, austere beauty to it, and it raises an obvious question. If the universe can pop into being from nothing, what determines the laws of quantum mechanics that permit this? Are those laws themselves eternal? Do they exist before the universe? If so, in what sense is there nothing before the Big Bang? Vilenkin has been characteristically blunt about this. The laws of physics, he argues, are not things that exist in time or space. They are mathematical structures. They don't need a place to exist any more than the number 7 needs a place to exist. The universe tunneled into being according to these laws, and the laws themselves are timeless, spaceless, causeless. Whether this counts as an answer or a very sophisticated way of saying we don't know is a matter of philosophical temperament. And that brings us to the current state of the field. Right now, as of today, the question, what came before the Big Bang, has at least 6 serious mathematically developed, partially testable answers. 1. Nothing. The question is meaningless. Hawking's no-boundary proposal. 2. Another aeon, a previous universe whose far future became our Big Bang through conformal rescaling. Penrose's CCC. 3. More inflation, an eternal self-reproducing multiverse in which our Big Bang was a local event. Guth and Linde's eternal inflation. 4. A brane collision, 2 membranes in a higher dimensional space that periodically collide and rebound. Steinhardt and Turok's cyclic model. 5. A contracting universe that bounced. Quantum geometry prevents the singularity and turns collapse into expansion. Loop quantum cosmology. 6. Nothing, but a different kind of nothing. Quantum tunneling from absolute nothingness. Vilenkin's tunneling proposal. Each of these answers has strengths, each has weaknesses, each has implications that would fundamentally change our understanding of reality if confirmed. And the terrifying, exhilarating truth is that we might be within a decade of distinguishing between some of them. The next generation of CMB experiments, CMB-S4, a ground-based array of telescopes at the South Pole and in the Atacama Desert, and Lightbird, a Japanese-led space mission, will measure the polarization of the cosmic microwave background with sensitivity orders of magnitude beyond current capabilities. If primordial gravitational waves exist at the levels predicted by the simplest inflationary models, these experiments will find them. If they don't exist, the upper limit will tighten to the point where many inflationary models are ruled out and alternatives like the cyclic model and LQC gain significant ground. LISA, the Laser Interferometer Space Antenna, scheduled for launch in the mid-2030s, will detect gravitational waves directly from the early universe, not imprinted in the CMB, but propagating as ripples in space-time. The spectrum of these waves carries information about physics at energy scales far beyond the reach of any particle accelerator. If the big bounce happened, LISA might see its signature. If brane collisions occurred, they would produce a distinctive gravitational wave background. These are not speculative possibilities. They are calculated predictions with specific numerical values that can be compared to data. And beyond LISA, even more ambitious proposals are being developed. The Big Bang Observer. The Decai-Hertz Interferometer Gravitational Wave Observatory. Concepts that exist today only as papers and proposals, but could, within our lifetimes, open a direct observational window onto the first instance of the universe and whatever came before them. The tools are almost ready. The theories are waiting. And the people who built those theories, some of them old now, some of them dead, some of them young and just beginning, are all asking the same question they've always asked: what really happened at the beginning? We've heard from the physicists. We've followed their arguments, their rivalries, their obsessions. Now it's time to step back and ask, what does all of this mean? Not for physics, for us, for anyone who has ever looked up at the night sky and felt the weight of the question pressing down. That's where we end this story. And it starts with something Roger Penrose said in an interview when he was 93 years old, half blind, still publishing papers, still fighting for his concentric circles, still absolutely certain that the universe remembers what came before. When Roger Penrose was asked at 93 why he kept working on CCC despite the skepticism of his peers, he said something that I haven't been able to stop thinking about. He said, "I'm not trying to be right, I'm trying to see what's there." That sentence contains everything. Not, "I'm trying to prove my theory." Not, "I'm trying to win the argument." I'm trying to see what's there, as if the answer already exists, written in the structure of reality. And his job, the job of a physicist, is simply to look carefully enough to read it. And here's the thing. Every single person in this story would say the same thing. Hawking wasn't trying to shut down a question for the sake of shutting it down. He was trying to see what the mathematics of quantum gravity actually implies about the boundary of time. Guth wasn't trying to create a multiverse for the fun of it. He was trying to see what the physics of scalar fields actually does in an expanding universe. Steinhardt wasn't trying to be a contrarian. He was trying to see whether the theory he helped build actually holds up under scrutiny. And when he concluded that it didn't, he said so, even though it cost him. These are not people playing games. These are people who have spent their entire lives, 30, 40, 50 years, on a single question. A question that most of the world considers unanswerable. A question that many philosophers consider meaningless. A question that, if we're being brutally honest, might never be definitively answered within any of their lifetimes. And they kept going anyway. I want to sit with that for a moment, because I think it tells us something important not just about physics, but about what it means to be human. We are a species that emerged on a small rocky planet orbiting an ordinary star in an unremarkable galaxy. We have been around for roughly 300,000 years, a cosmic eye blink. We developed science about 400 years ago. We discovered that the universe is expanding less than 100 years ago. We mapped the cosmic microwave background for the first time in 1992. That's 33 years ago. In the span of a single generation, we went from not knowing the CMB existed to arguing about whether we can see the fingerprints of a universe that preceded our own. That is extraordinary. That is the most extraordinary thing our species has ever done. Not building cities, not splitting the atom, not going to the moon. The most extraordinary thing is that a bunch of slightly evolved primates on a rock in space looked at the faintest light in the universe and asked, is there a message in this? Is there a memory? Is there a ghost of something older hiding in the static? And the answer might be yes. Let me lay out where we actually stand, clearly and without hype. We have 5 major frameworks for what came before the Big Bang. Hawking's no-boundary proposal says the question dissolves. Penrose's CCC says there were previous aeons. Guth and Linde's eternal inflation says there was, and is, an infinite multiverse. Steinhardt's cyclic model says there were previous cycles of brane collisions. Loop quantum cosmology says there was a contracting universe that bounced. Of these 5, 2 make sharp, testable predictions that current or near-future technology can probe. The first is the tensor-to-scalar ratio, the amplitude of primordial gravitational waves. Simple inflation predicts a detectable signal. The cyclic model and LQC predict little or no signal. CMB-S4 and LIGHTBIRD will measure this within the next decade. If they find gravitational waves, simple inflation gets a massive boost, and the cyclic model is in serious trouble. If they don't, the field cracks wide open. The second is the large-scale anomalies in the CMB, the suppressed quadrupole, the quadrupole-octopole alignment, the hemispherical asymmetry. These are real features of the data that the standard inflationary model does not naturally explain. LQC offers a natural explanation. CCC offers a different one. If next-generation experiments confirm and sharpen these anomalies, the case for a pre-Big Bang universe strengthens considerably. Beyond the CMB, gravitational wave observatories like LISA could detect a stochastic background of gravitational waves from the very early universe. Different models predict different spectra. The cyclic model predicts a blue-tilted spectrum. Inflation predicts a red-tilted one. LQC predicts specific features related to the bounce. These are distinguishable in principle with sufficient sensitivity. So the answer to, will we ever know what came before the Big Bang, is not no. It's maybe, and sooner than you think. But I want to be honest about something. Even if the experiments deliver perfect data, even if one framework clearly fits and the others clearly don't, there's a deeper layer of the question that physics alone might never reach. Because here's what none of these theories explain: why there is something rather than nothing. Hawking's no-boundary proposal describes a universe that simply exists as a self-contained geometric object. But why does that object exist? What breathes fire into the equations, as Hawking himself once asked? Guth's eternal inflation describes a process that generates universes endlessly. But why does that process exist? What is the ground state of reality? Penrose's CCC describes an infinite sequence of aeons, but why is there a sequence at all? Steinhardt's cyclic model describes branes colliding forever. But why are there branes? Why is there a bulk? Why is there anything? These are not scientific questions in the usual sense. They may not have scientific answers. They belong to the borderland between physics and philosophy, between mathematics and metaphysics. And the honest answer, the answer that every physicist in this story would give if you pushed them hard enough, is we don't know. We might never know. And that's okay. It's okay because the value of the quest does not depend on reaching the destination. Every one of the frameworks we've discussed, even if it turns out to be wrong, has taught us something real about the universe. Hawking's no-boundary proposal taught us that quantum mechanics can be applied to the universe as a whole, that the wave function of the cosmos is a meaningful concept. Penrose's CCC taught us that conformal geometry might connect eras of cosmic history in ways we hadn't imagined. Inflation taught us that the first fraction of a second after the Big Bang shaped everything we see today, and that the quantum fluctuations of a microscopic field became the seeds of galaxies. Steinhardt's cyclic model taught us that alternatives to inflation exist and deserve to be taken seriously. LQC taught us that quantum geometry might resolve the singularity and open a window into a pre-Big Bang era. Even the wrong answers advanced our understanding. That's how science works, not by marching in a straight line from ignorance to truth, but by exploring a landscape of possibilities, ruling out the ones that don't fit, and gradually narrowing the circle of uncertainty. And the circle is narrowing. That's the key point. 50 years ago, the question, what came before the Big Bang, was not a scientific question. It was a philosophical musing, a late-night dorm room debate, a topic for theology or stone speculation. Today, it is a research program with competing mathematical frameworks, specific numerical predictions, and experiments being built to test them. In a single human lifetime, we have gone from "this question is unanswerable" to "we're building the machines that might answer it." That's the real story. Not Hawking versus Penrose, not Guth versus Steinhardt, not inflation versus the cyclic model. The real story is the one underneath all the rivalries and all the theories. The story of a species that refuses to stop asking. Let me tell you one more thing about the people in this story, because I think it matters. Stephen Hawking worked on the origin of the universe until the last weeks of his life. His final paper with Thomas Hertog was completed just days before he died in March of 2018. He was 76 years old. He had lived 55 years longer than his doctors predicted. He could not move. He could not speak without a computer. He communicated by twitching a single muscle in his cheek. And he spent his final days thinking about the boundary conditions of the cosmos. Roger Penrose, as I mentioned, is still working, still publishing, still analyzing CMB data, still looking for his circles. He turns 95 this year. His eyesight is failing. His body is failing. His conviction is not. Alan Guth is 80 and still teaching at MIT, still giving talks about inflation, still defending the multiverse with the careful, understated precision that has characterized his entire career. He never won the Nobel Prize, despite being nominated repeatedly. He says he doesn't mind. He says the work is what matters. Andrei Linde is 77. He lives in California now, far from the Moscow of his youth. He still gives lectures with the same theatrical intensity he's been famous for since the 1980s. In one famous video, his colleague brings him the news of the Bicep 2 detection, the one that later turned out to be dust, and Linde opens the door, hears the result, and his face transforms. Pure joy, pure wonder. The joy of a man who has spent 40 years on an idea and believes in that moment that the universe has finally confirmed it. The fact that the confirmation evaporated months later does not diminish that moment. It makes it more human. Paul Steinhardt is 73. He runs the Princeton Center for Theoretical Science. He still publishes papers on the cyclic model. He still argues against the multiverse with the same intensity that he's been bringing for 20 years. In interviews, when asked if the scientific community has treated him fairly, he pauses. He chooses his words carefully. He says that science is self-correcting, that the truth will eventually emerge, that he has faith in the process even if the process is slow and sometimes painful. Whether he fully believes this, or whether it's the diplomatic answer of a man who has learned the cost of being too honest, is something only he knows. These are the people who are trying to answer the oldest question. They are not mythological figures. They are human beings with egos and insecurities and mortgages and bad backs. They disagree with each other. They sometimes dislike each other. They have made mistakes and published retractions and chased dead ends. And collectively, over the course of 50 years, they have brought humanity closer to understanding the origin of everything than anyone in the entire previous history of our species. So here's where I'll leave you. 5 answers: no boundary, cyclic aeons, eternal inflation, brane collisions, quantum bounce. Each one is a different vision of what reality fundamentally is. Each one carries different implications for our place in it. In Hawking's universe, we exist within a self-contained bubble of space-time that has no outside and no before. There is a strange comfort in that, a completeness. In Penrose's universe, we are one chapter in an infinite book. Everything we build, everything we create, everything we are, will eventually fade to nothing. And from that nothing, a new chapter will begin. There is a strange beauty in that, a rhythm. In Guth and Linde's universe, we are one bubble in an infinite foam. Somewhere, right now, new universes are being born with different laws, different constants, different possibilities. There is a strange vertigo in that, an immensity. In Steinhardt's universe, we live between collisions. The Big Bang was not a birth, but a heartbeat, one in an infinite series. There's a strange reassurance in that, a continuity. In the universe of loop quantum cosmology, we are the rebound. A previous universe collapsed, reached the limits of quantum geometry, and bounced back into existence as us. There is a strange intimacy in that, a connection to something lost. I don't know which of these is true. Nobody does. And anyone who tells you they know is selling something. But I do know that the question, what came before the Big Bang, is no longer unanswerable. It's no longer philosophy. It's physics, hard mathematical testable physics. And the answer is coming. Maybe not tomorrow, maybe not this decade, but it's coming. Because that's what we do. We ask questions that seem impossible, and then we build the tools to answer them. We've done it before. We'll do it again. The universe might have forgotten what came before, but we are very, very good at remembering. Thank you for staying with me through all of this. If this video made you think, if it made you look up at the sky a little differently, share it with someone who might feel the same way. And if you want to keep going deeper into the biggest questions in physics, subscribe. There's a lot more to explore, and I think we're just getting started.